Hello everybody. Here's the first video out of 4. I'm going to give you 4 short videos instead of one great big humongous long one. And we're going to look at what derivatives have to do with shapes of graphs. So let's dig in. We already know about first derivatives. We know when the first derivative is positive, the graph is increasing, and when the first derivative is negative, that the graph is decreasing. But what does the second derivative tell us? Here's an everyday example, just using words, of the second derivative. Inflation is slowing down. This does not mean that prices are decreasing. Prices aren't going down. We still have inflation, so prices are still rising. They're just not as rising as quickly as they were before. So this slowing is modifying inflation, and inflation is modifying prices. So prices are still going up, but they're not going up as fast as they went before. And so you can see that the second derivative is putting kind of a little curve into the graph. Okay. It's like a force that forces that graph to bend down a little bit. And if you think about it, that kind of makes sense. We talked about second derivatives in relation to acceleration, and Newton's law says that force is mass times acceleration. And the acceleration is what keeps something from going in a straight line. It forces it to bend a little bit. So it's the same kind of idea here, just more general. Okay. And so when we think about first derivative and second derivative together, there are 4 possibilities, depending on whether first derivative is positive or negative, and whether second derivative is positive or negative. Okay. When first derivative is positive, the function is going up, but when second derivative is also positive, that means it's going up faster and faster. So that means that the graph looks kind of like this. It's got a little concave side. That's called concave up. So increasing and concave up. Now let's look over here. First derivative is still positive. Okay. But second derivative is negative. That's our inflation is slowing example. So the graph is increasing, but not as quickly as it increased before. You can see the concave side is down. Okay, that's called concave down. So first derivative positive is increasing. First derivative negative is decreasing. Let's see what second derivative does here. If first derivative is negative, then the graph is going down, it's decreasing. Second derivative positive means that it decreases more and more. It decreases less and less. It decreases less and less. We have a negative derivative, but it's increasing because positive. So it's increasing less and less. It's getting closer to 0. So over here on the left, my graph is very, very negative, and here it's not so negative. It's closer to 0. It's larger than it was on the left. I'm going to take those away. And again, the graph has a concave side up. And then finally over here on the right, if my graph is decreasing, but it's decreasing less and less, okay, the second derivative is negative, so that means that the graph is getting more and more negative. So it looks like that, and the concave side is here. So what's happening is when f double prime is positive, this is called concave up. It looks like if these were the arms of the graph on the ends here, it looks like they want to hug upwards. Think about which way you would want to hug. if those were your arms. So the hug goes up when the F double prime is positive, and concave down, the hug goes down when F double prime is negative. And basically, any graph can be made out of those 4 different pieces of graph, just put together in different places. Now, it's not so important for us to be able to graph these functions using those pieces. It used to be a long time ago, but now we've got technology to do that. But in particular, we're going to use this to analyze graphs as we go on. So I'm going to move away from that, and I'm going to talk about what are called extrema on a graph. But keep an eye on this for F prime and F double prime, because we're going to come back to that in a future video. Get rid of that and make a new slide. Let's talk about extrema. That's the plural. The singular is extremum, okay? And these are the high and low points on a graph. And we've got 2 kinds. We've got some that are called local extrema, also called relative extrema. You'll see either word. And that's the highest or lowest point in just a small neighborhood of the graph. And neighborhood is a technical word. That's not just a made-up word. Let me draw a couple of pictures here with a graph. So maybe I have a graph that looks like this. Okay. Here is a local maximum. Here is another local maximum. Right here. Here is another local maximum. And here is another local maximum. So in just one little spot right around each of these points, it's the highest point just in that one little neighborhood. Okay, here are some local minima. Here's one, here's one, here's one. So it has, this particular graph has got 3 local minimum and 1 local maximum. Oh, no, excuse me, and 4 local maxima. Okay. We can see from here that either f prime equals 0 or f prime does not exist. And that's what we talked about the other day when we talked about Rolle's theorem. Okay, so when you have a local maximum or a local minimum, the first derivative is either 0 or the first derivative doesn't exist. We also have some that are called global extrema, which are also sometimes called absolute extrema. And that is the very highest or lowest point on either the entire graph, or very often we're only looking at a portion of the graph. Maybe we're looking at the graph only over a closed interval. So very highest or lowest point. And that's usually within a particular range, which is usually a closed interval. So for global extrema, we very often restrict the domain. And you'll see why next week when we start to look at word problems, real life situations. So let me just draw a graph, and because we're usually doing this over a closed interval, I'm going to draw a little closed interval down here. And here's my graph. Maybe it looks like that. And it comes up, and it comes down, and it comes up. And so if I look at the graph just in that range, I can see a local local max right there, but my local min is at an end point of the domain, and that's very possible. Okay, so when we have global extrema, we have to look at the places where f prime is equal to 0, where f prime does not exist, or possibly an end point of our domain. Now, when we find where f prime equals 0 and f prime does not exist, those are called critical values. Okay, sometimes they're called critical points. Most people call them critical values. So I just wanted to let you know those words. Critical values are where the derivative equals 0 or the derivative does not exist. Your x values, where f prime of x equals 0 or f prime of x does not exist. And these are possible local extrema. Happen at critical values. They're not guaranteed to be local extrema. Okay, and we'll see some examples of that in the next video, but I just wanted to make sure that you knew what critical values were. We do need to test to find out if we have a local minimum, a local maximum. Okay, and the same for the global. We need to test to see. So that's it for this video. The next video we'll talk about local extrema, how to find the test, how to make that test, and how to identify them.